Yes, this is a talk on MiRitH, joint work with authors listed here. So let me start with a small overview on the talk. So first we will talk about the foundation of MiRitH. So as the name suggests, it's based on the hardness of the min-rank problem. And then we will define the min-rank problem and see its relation to the rank metric decoding problem. Then we will quickly outline the approach. I will just recall quickly the MPC in the head paradigm to fit it into the context of MiRitH. So we will start from the MPC protocol, which allows the parties to verify that they share a min-rank solution, then construct zero-knowledge proof of knowledge via the MPC in the head paradigm, and then apply the Fiat-Shamir transform to get the signature scheme. And last but not least, we will talk about the parameters, their security, and the performances we achieve. So let's start with the min-rank problem. So we have min-rank, but in min-rank we have given an integer r and k+1 matrices, m0 to mk, and we're asked to find the linear combination of those matrices that has rank smaller than r. And often you hear like that min-rank based schemes fall into the realm of rank metric decoding based schemes, and this is because you can also give a slightly different formulation or interpretation of the problem, where you see or consider the matrix G, which has as rows the vector representations of these matrices, and this is a generator matrix for a code, and you interpret the M0 as a faulty code word in the sense that the code word is a linear combination of those matrices, which is alpha 1 to alpha k times the generator matrix, plus the error, where the error is the low rank matrix that you have to find. So finding the low rank matrix is actually decoding the faulty code word defined by M0. In our construction, we use random instances, meaning all matrices, secrets, and the random and the matrix E are chosen at random. Okay, let us quickly review or recall the MPC in the head paradigm. So we start from a MPC protocol on n parties. So we restrict ourselves here to additive shares as they are used in MiRitH. So every party is given a function f and a value z and a share xi of x, such that the sum over all the shares is equal to x. And the goal is to verify if they indeed share x, such that f of x is equal to z. So if they think after the execution of the protocol, exchanging some messages and performing some computations, they should accept if they think they do share and reject in case they don't. And we have this false positive rate. You remember there is a probability that the parties accept even though they don't share x. But this should be rather small to make it somehow a reasonable protocol. And of course, we have a zero knowledge property, so there's no information about the xi's leaked to the other parties. So once we have such an MPC protocol, we want to construct a zero knowledge proof of knowledge, in which a prover P wants to prove knowledge of a value x, such that f of x is equal to z to a verifier, but of course without revealing x. So, and we recall this works by the prover preparing the inputs to the MPC protocol, committing to those inputs, the verifier sampling some first challenge to provide randomness for the MPC protocol, which is then simulated by the prover. Again, he commits to the views of and intermediate states of this MPC execution. The verifier samples a second challenge I star, provides it to the prover, and the prover reveals all corresponding views that are not related to this I star's party. And he gives some auxiliary information, which is like the outputs of the computation of the I star's party, to enable the verifier actually to recompute all the commitments and actually verify that the simulation of the MPC protocol accepts. Okay, this is how the MPC, how to arrive in the zero knowledge proof of knowledge. Then we repeat the protocol to obtain some negligible or small soundness probability. And on top of that, we apply the Fiat-Shamir transform to obtain a signature scheme. And this is how the MPC in the head paradigm works to construct a signature. Now let us look into how does it work in MiRitH. So what's the design rationale for MiRitH? So in MiRitH, we use the Kipnis-Shamir modeling. What's the Kipnis-Shamir modeling? It basically models min-rank as a bilinear system. And this looks like this. But it's not that important that it's a bilinear system. What's more important is solving this system, so finding a beta and a k that fulfills this system, is actually solving min-rank. Solving min-rank in the sense that this matrix on the left, defined by the linear combination, is actually of rank smaller than R. So this means that the beta i's actually solve the min-rank problem. So we call them alpha i's again, as in the definition of the problem. So we substitute them here. And then we call this matrix M alpha. And we split it into its first n minus r rows and call this matrix columns, and call it M alpha L for left. And then the last r columns we call M alpha R, and then we can construct this identity here. And now what we have is that knowledge of a min-rank solution alpha is actually equivalent to knowledge of a k, such that this relation is satisfied. Well, this doesn't look like we achieved much because we extended somehow the secret key to alpha and k now, because to verify this relation, you actually need to be able to compute M alpha, which requires knowledge of alpha. But on the other hand, and which is the good thing, is that we have a linear relation which we can somehow verify via an MPC protocol, which is very well suited for this purpose. So how does this work? So again, we construct shares of alpha and k, which now are the secrets, and distribute them to the MPC parties. And then we want that this MPC protocol verifies that the parties indeed share alpha and k, such that this identity is verified. And again, they accept if they think they do, and otherwise they reject. And no information on the shares should be leaked. And in MiRitH, we do this via an MPC protocol for matrix triplet verification. So this such a triplet is X, Y, and Z, triple of matrices, which fulfills X times Y is equal to Z. So there's a known protocol with some improvements that we use, and this works as follows. So the parties initially get shares of this matrix multiplication triplet and some C and A. So C and A are here auxiliary matrices fulfilling C is equal to A times Y. So you can easily construct it initially by just choosing an A and then setting C to A times Y. And then they perform the following MPC protocol. So first they select a random matrix R. So this matrix has to be equal for all the parties, but in our case it will be the first challenge of the verifier. And then they compute this SI, as shown here. They broadcast it such that everyone can compute the S, and compute these VIs, broadcast, and obtain the V. And if you use the relation between the matrix verification triplets here and plug it into the VI, then you will see that everything cancels out if those relations are fulfilled, meaning V is equal to 0 in case those things are really, the prerequisites are met, meaning we have a correctness. So if everything is as desired, then the parties accept. And you can actually show that the parties, if this is not the case, the parties accept with probability q to the minus t, where t are the rows of the number of rows of R. So by choosing an appropriate t, we can lower this probability to something that is not that relevant anymore. On top of this, we then, or going from this MPC protocol, we then apply the full MPC in the head machinery to obtain our signature scheme. So in summary, we use the Kipnis-Shamir modeling to obtain a linear relation that allows us to use the MPC protocol for matrix triplet verification. Then we apply the MPC in the head paradigm with all its modern techniques, including the hypercube and seed trees and initial hashing of commitments as detailed yesterday by Thibaut. And finally, we apply the Fiat-Shamir transform to arrive to conclude with the signature scheme. So this is how MiRitH is constructed. Now let us look into security and performances and parameters of the scheme. So the min-rank problem is actually quite well studied due to its applications in cryptanalysis, meaning there are many problems which can be somehow formulated as a min-rank problem, and hence better attacks on min-rank imply better attacks on these problems. So there has been quite some effort on improving attacks. And roughly, the best attacks can be categorized as follows. So there is a kernel search algorithm, which is a somewhat combinatorial technique where you guess vectors in the kernel of E. And if you know enough of these vectors, you can solve for E. Then there is a support minus modeling, which models the min-rank relation as a bilinear system, similar to what we have seen with the Kipnis-Shamir modeling, but it is a slightly different modeling, and then uses some algorithms to solve these bilinear systems. And there is a big K attack, which relies on guessing entries of E, and then solves for E. And on top of that, you can apply like a hybrid technique, which guesses some of the alpha i's and some of the kernel vectors. And then this relates to a reduced dimension min-rank instance, so min-rank with smaller k, smaller m, smaller n. And then you apply one of these three algorithms to solve this reduced instance. So now let us look into the parameters and their security. So we provide two sets, an A set and a B set. So the A set is meant to provide or to match the NIST security guarantees quite precisely according to today's best known algorithms. And a B set, which is slightly more conservative. So we have some security margin in there for to mitigate the effect of attack improvements. And those are the complexities of the just mentioned attacks on those parameter sets. So we see for the category A set, the support minus modeling is the best attack, which is somehow one of the most recent advancements. And the B set is chosen such that the kernel search, which is like a more naive attack, is the best or yields the best complexity, like somehow supporting a bit the conservative, that this set is like more conservative. Last but not least, let us look into the performance of these parameter sets. So we have, again, for like it's quite usual for the MPC in the head schemes, is short and fast variants. Short for shorter signatures, but with slightly slower signing and verification, and faster but bigger signatures. And here we have the same for the B set. We see we obtain slightly larger signatures, but in terms of signing and verification, roughly the same performance. Like only on the fast set, it's like quite reasonable, more reasonable difference. And we see that also here, as yesterday mentioned, like in the 5 to 10 kilobyte range, we lie also like somewhat on the smaller end in terms of signature size. Regarding limitations and advantages, the scheme fulfills the same as usual MPC in the head constructions, meaning we have a quite solid security foundation with relying on unstructured problems. But on the other hand, we do not achieve the performances of lattice-based schemes, basically. Thank you very much.